In the previous videos, we saw that the definition itself, the small details of the Turing machines, don't really actually matter in the definition because no matter what we choose, we can always simulate it efficiently with the simplest Turing machine. And when I talk about the simplest Turing machine, as a reminder, I talk about this machine that can only read and write sequentially in one infinite tape of zeros and ones. This is the simple Turing machine. And when I talk about the small details, it could be the number of tapes. Here we have just one tape. The alphabets. Here we have just the alphabets that is just 0 and 1. Or even the way how we can read things. Here we are only allowed to read from right to left, but we can say that we are allowed to read any position that we want. But here we stick with the sequential definition. And all these little definitions, all these small details don't matter because no matter what we choose, we can always efficiently simulate it. And this is why now we need to prove that a K-tape sigma alphabet, so a Turing machine that has access to K read and write tapes and a general sigma alphabets, this Turing machine can be efficiently simulated by the simple Turing machine. And so how are we going to do it? I propose the following outline. First, we're going to prove that we can simulate a Turing machine with a general sigma, a general alphabet, and just one tape. And secondly, using this definition, so we're going to prove that we can simulate this thing with this thing efficiently, and then we're going to prove that we can simulate a Turing machine with an alphabet sigma and with K-tapes efficiently with this definition. And because efficient means in polynomial time, if we can simulate this in polynomial time of this, that can simulate this in polynomial time, because combining polynomials just still gives a polynomial. Well, if we prove in this way, we will still at the end achieve an efficient simulation globally. So let's already start. First, we want to prove that we can simulate any kind of alphabet with just a binary alphabet. And the idea is that, for example, if we take sigma that is just equal to 0, 1, 2, 3, we can assign an encoding, a binary encoding to each single element. So we can kind of translate each element into just a sequence of zeros and ones. We can say that 0 is mapped to 0, 0, 1 to 0, 1, 2 to 1, 0, and 3 to 1, 1. This is a very easy translation, and actually this matches with the binary version of the number. And using this translation, we can convert all the rules that the original Turing machine reads into rules that our simple Turing machine can read. For example, let's say that we have a rule here, Q5, that says, if I read 0, let me write a 3. And if I read a 2, I want to write a 1. So now, of course, this rule is done in just one step by the Turing machine M. But it's impossible to read it for our Turing machine M prime, that is the simple one, because we don't know how to read 3. We don't know what is a 3. We don't know what is a 2. We only know what is 0 and 1. And so we're going to translate it into something that is understandable by our machine. We can say here that the state Q5 is equivalent of, if we read 0, 0, we need to write 1, 1. And if we read 1, 0, we need to write 0, 1. And so now we can read a 0, we can read 1s. It's better for our machine, but still, we cannot read two things at a time. We only can read one single bit at a time. But if you think about it, you can always enforce this behavior. For example, we can imagine that we create a state, let's say Q5 read, that says, okay, now I enter the state Q5, but I still need to read. And then we'll enter the state Q5, and equivalently with the writing process. So just we'll need to create more states, and reading will not be done in just, or even writing will not be done in just one step here. We will use approximately 2 steps with the Turing machine M prime. And so if we can do the process in just, let's say, 10 steps with our bigger Turing machine, it requires 20 steps here. And in general, if you have a bigger alphabet, let's say an alphabet that has a size L, we know that we need log to L bits to encode each single element in a unique way. And this is because we know that there exist 2 power k strings of k bits. And so if we want that 2 power k was equal to L, then we will have that k is equal to log 2L. And so in general, if you want to simulate a bigger Turing machine with an alphabet of size L, you can do it, but it will take for each step log 2L steps. And so we can say that we can simulate a Turing machine with a general alphabet and 1 tape with the binary one that we will just write like this, such that for each single step in the original Turing machine, we take at most log 2L more bits. Of course, we can take the ceiling because we need an integer number of bits times the initial running time. And so, because of course this is just a constant factor, we can already say that this is big O of the initial time. And of course, this is just the time itself, so it's indeed polynomial. So this step was really easy because you just take the translation of the general alphabet into a binary one. But now, the second step will be a bit more difficult. Let's say that you have a Turing machine that has k tapes, and each single tape can basically just read anything that belongs to sigma. And we want to simulate this Turing machine that has access to the k tapes with just one single tape. Of course, each cell can contain also something in sigma. How can we do it? Well, the idea comes from, if we have k infinite tapes, we can try to find a way to fit the k tapes into just the one infinite one. And it's because if we talk about infinities, k times infinity is still equal to the infinity. And so we can fit the k tapes into just a single one. Let's, for example, say that we have k equal to 3. We can assign each cell a corresponding tape. For example, we can say that this spot corresponds to the tape number 1. And then we can say that these spots correspond to the tape number 2. And you guessed it, these places correspond to the tape number 3. And so if we just do this infinitely, well, because of infinities, we'll be able to fit the k infinite tapes into just the single one. But now there is also another problem, which is in this setup, we know that we can have a head here, and that we can read and write at the same time, even if the heads are at different positions. And in our single type Turing machine, we only have one single head. So it's impossible to memorize the head here, and the head here, and the head here, for example. It's impossible. But because we know that increasing the size of the alphabet doesn't impact the complexity of our simulation, we can use a trick and we can extend our alphabet. We can double it and add new elements. For example, let's say that we have just the smallest alphabet, just 0 and 1. We can extend this alphabet into having 0, 0 hat, 1, and 1 hat. For each element, you just create another version of it with a little hat on it. And so what we can do is that instead of remembering with just our head the place where we need to read and to write, we can write it so that we can just say, okay, I know that the head for these tapes was here, and I can continue and just look for it. So for example, let's say that we are in this setup. We have 3 tapes, 1, 2, 3, that have 0, 1, 0, 1, 1, 1, and 1, 0, 1. Why not? And so we can fit these tapes into this one. Here we have 1, 0, 1. The second one will be 1, 1, 1. And the third one will be 1, 0, 1. And we can imagine that we are in a setup where the heads are here, here, and here. And so the heads would be here, here, and here. But as we said, it's impossible to have 3 heads. We only have 1. And so instead of doing this, we'll just replace the places with a special symbol here. We're going to put a hat here, we're going to put a hat here, and a hat here. And so for each color of the tape, we're just going to have exactly one element that has a hat. And so when we're going to read things, we're going to look for the head. We're going to try to look for it. Like if we want to read in the first tape in the original Turing machine, we will need to travel the tape and to look for, okay, now we know that the head is here. And the same for the third tape, for example. We will just look for it. Is it here? No. Is it here? No. It's here. And so I need to replace at this point. And so if I need to move the head, for example, here, left to right, I know that I will have to replace this with just a normal one. And here I will put a hat here. And so this is how we're going to memorize the heads in the original setup. But what is the complexity of this? Well, for example, we can imagine that we have a head here and we have another head very far away. In this setup, in the original Turing machine, we can read this in just one single step. But in our version, we need to go here and then to travel all the way until here. And so we don't take just one step. We need to just, of course, if the head is here, we do it in one step, but then we need to travel all this distance to deal with this element here. And so what is the most far away distance that we can travel? Of course, it is at most Tm of n, because we can never go more far away than the number of steps. Of course, let's say that we have a running time of 3 steps, we cannot write 4 elements because it will require at least 4 steps. So this is the most far away distance. So at most, if we have 2 tapes, I need to travel this distance twice. And if I have k tapes, I need to travel this distance k times. And so for each single step, I travel at most k times this running time. In a more formal way, we know that the Turing machine here that only has access to sigma and one single tape takes at most k times the initial running time times the number of steps. So at most this number. And so this is equal to, because this is constant, we can just not write it, to the initial running time squared. And so this simulation can do it efficiently because this is just polynomial. And so we saw that even if we have k tapes on one side and just one single tape, we can simulate it by trying to fit all the infinities into just our infinities, by extending our alphabet for remembering the heads. And so for each single step, when we can just memorize the heads in the original setup, we will need to travel all the way to check the heads, to replace the things. And this could be done. It's slow, but it's still efficient because we only care about polynomial factors. Here, we know that this is indeed polynomial in the initial running time. So that's it. We are done.